All right, so what information does the function tell you? That's what? What does the function tell you? The function. Now, what does the function tell you? What does the function tell you? I'll give you a clue. There, what does f of x tell you? It does not say the slope. It tells you the what?
Y slope?
Not y slope.
Oh, no, y.
It's right here. These two things are synonymous. This is the coordinate. It's the y coordinate. That's right. F of x is the y coordinate. F of x is always the y coordinate. That's what it represents. So when you calculate f of x, every single f of x you ever calculate in your whole life is going to land on the y-axis somewhere because it's telling you the y value of the function. So f of x is synonymous with y, where that represents the y coordinates. Another way of looking at that is it's the height. So that's the height above the y-axis. So f of x is the height, it's the y-coordinate, and I think we said something else about it, just that it's the output of the function. Okay, so then what does f prime of x tell you? What does f prime of x tell you, Sarah? That's the slope. So if I go on here at any given point and I draw a little tangent line indicator, that little tangent line, if I wrote m equals, I could write m equals f prime of x. So the slope at any given point along this graph is f prime of x. And if you plug in the next value, it's going to find that coordinate and then tell you the slope of that coordinate. Okay, and then finally, what does f double prime of x tell you? Okay. Yes, the concavity. So at any given point, if I choose a point and I want to know what's going on right there generally for that curve. So like right here, is it concave up or down? Concave up. So if I were to calculate for that point, f double prime of x, I don't know the exact number that it's going to give me, but it's going to give me a positive value. And then if I were to go over here and choose this x coordinate and calculate f double prime of x, I don't know exactly what value it's going to give me, but this here is concave down. So it's going to give me a negative value. I don't know what negative value, but it'll be a negative value. Okay, so that's what f prime and f double prime tell us. So now how do you find a maximum or a minimum of a graph? And I'm going to write that out as instructions. So to find a flat spot, which in other words is a max or a min, but you know it could be more than just a max or a min. It could be a max, it could be a min, it could be a transition point, or it could just be a flat portion of the graph. So how do we find a flat spot? Yeah, set the derivative equal to 0. So set f prime of x equal to 0 and solve for x. And that's going to find all the x values where there is a flat spot. You still have to plug that x value back into the original function to find out where that actual coordinate is. Where is that coordinate? So you'd set f prime of x equal to 0, solve for x. That'll tell you the x location of a flat spot. And then you'd have to plug x into the function, and that would tell you where that coordinate is. Okay, then how do you find an inflection point of a graph? What is an inflection point?
It's the point on the No. It's the transition point between concave up.
Right. Yeah, visually speaking, we can most easily recognize an inflection point if it's going from concave up to concave down. However, technically speaking, an inflection point is anywhere the concavity is 0. So just like you'd set f prime of x equal to 0 to find flat spots, to find an inflection point, what would you do? Find inflection points. We would set f double prime of x equal to 0. And that would tell us where those points are, where the concavity temporarily goes to 0. So obviously, if you're transitioning from concave up to concave down, since this is concave up and this is concave down, there would have to be a moment where you pass through 0. Just like on a number line. If you're on a number line and you're over here on the positive end of the spectrum, and then you want to get to the negative end of the spectrum, you have to pass through 0 to get there. And so definitely switching from concave up to concave down, you must pass somewhere through 0. And that would be an inflection point. But it is possible for a graph to maybe be concave up and then go flat for a second and then go concave up again. And in that case, you could also go from concave up to concave up, but you could pass through a 0 where there's no concavity, where it's not bent. Okay, well, those are our 2 main tools, folks. We set f prime of x equals 0 to find flat spots, and we set f double prime of x equals 0 to find inflection points. What questions would you like to ask? Okay. Did you all enjoy the rain this morning? Leonard? You didn't enjoy the rain this morning?
So when I went on to more to be 2.5.
Yeah. I'm very sorry for that. Josh told me that this morning, and I already opened it back up again. Yeah, no, it wasn't just
Thanks,
you.
Josh.
All right, anybody else? No. All right, well then let's finish up what we were doing in section 2.6, as well as go back to do number 4. Number 4 is an exciting problem. And then we'll proceed. So here we are, today is February 21st. We'll finish 2.6 and then start 2.7. We still have many more class periods to go before we have a test. Then you have spring break. Got 2 cute jokes for you. Wait, isn't it today Thursday? I'll tell you both. How about that? A little bonus. I'll tell you both jokes. What do you call a bear without teeth? A gummy bear. Okay, and then this is a classic joke. Why did the scarecrow get a promotion? Or why did the scarecrow get a Nobel Prize? He was outstanding in his field. Yeah, that's a good one. I know you'll tell your friends and family about that. Okay. Oh, I didn't turn that on. So, I think we stopped here. Yes?
Where's number 9? And
I might have just deleted it and not renumbered all the numbers to be in order. There's a good chance I just did that. Okay, so here we are, folks. A problem like this is purely conceptual, doesn't take much time or computation. It just says, at the point shown, which is true. Or is it? So they're asking for the derivative value. Is it negative or positive? And the concavity value. Is it negative or positive? So before you sit there looking through all those different possibilities, let's just look at it and think about it for ourselves. What is the derivative value right here? F prime is equal to negative something. Right, the slope is negative, it's going down, so for sure we know that f prime is negative. And now let's also consider that point and look at the concavity right here. So f double prime is also negative. So that's it. We're just looking for an answer where it says f prime and f double prime are both less than 0. And that's it. It's purely a recognition problem where you can say what's going on the graph. There's no computation necessary. Questions about that? All right, so that's number 8. Yeah, correct, Josh. No number 9. You can fill in your own number 9 if you like. All right, number 10. We have some graph here, and it says again, determine the signs plus minus is 0 of y equals f of x. So shown in the graph, this is f of x. So this is our original function. And you'll notice that we know that this is x equals 2. We don't know anything else, like I suppose 0 could be here, and that could be 0, 1, 2, or it could be that 0 is way over here. I don't think that it really matters what anything else is doing or where the other numbers are. We're just looking at that part of the graph, and it says at the exact moment when x is 2, what's happening? So first of all, what's the sign of the actual function? And we can't assume this is the x-axis. Is that fair that we can assume that's the x-axis? Yeah. So, hey there, Jared. So what is the function value itself? Is it positive, negative, or 0? Definitely negative because it's below the x-axis, so f of x is negative. So we can just say f of 2 is negative. Or you can write f of 2 is less than 0. That might be a little more precise than just writing equals a negative sign. And what about f prime of 2? What is the slope doing right then at that moment? It looks, yeah, I mean, it looks flat. I think any reasonable person would agree that it's flat. I mean, someone might say, it could be increasing if you zoomed in far enough, and that's true, but I think most reasonable people would say, hey, f prime of 2 is 0. And then what about the concavity right there? Definitely over here the concavity is negative. And definitely over here the concavity is positive. So, I mean, it could be that we're at the transition point. That's another reasonable assumption. I'm sure somebody, a heckler in the back of the room, could say, no, the inflection point's actually here, and right here it still looks positive. You know, there's a lot of arguments you could make, but it appears as though that's an unmet portion of the graph. So we would just say f double prime of 2 is also 0. Does that seem reasonable? We're just speaking off the cuff, casually, amongst friends. Those appear to be the correct answers. Okay, 2 more here. Number 11. Tell you the truth, you can cross out number 11, and I'll make sure to erase any questions like that from online. I'm just not a big fan of that question. You can cross out number 11. And so number 12 is just like one you've already done. So everybody go ahead and do that one. Then we'll consider number 4. Did anyone else get A? You know, presuming that that's A, B, C, D. Did anyone else get A? Is the slope is definitely positive. So you could just go through and cross out the 2 negative slopes. And then the concavity is negative, so you can cross out the 2 positive concavities. And that leaves us with option A. All right. This next question we're going to do is we're actually going to flip back to number 4. I saved the best for last. What's that?
Why is it close to the front?
Why is what close to the front? That's a good point. See, I should rearrange that and put it towards the back. See, I've done some rearranging, and then every year I tinker with it a little bit more. So the first thing we're going to do, well, we can just read through the question. All right, let's just read through the question and see what they're asking. It says, consider this function x squared e to the 10x. Now, you know, this is a multiplication function. So you've got x squared, which looks like this, being multiplied by the function e to the 10x, which looks like this. And so when you multiply those 2 functions together, definitely over here, they're both increasing quite a bit. So we'd expect a graph that ends up going up like that. But over here, we're multiplying the tail of a parabola times the tail of an exponentially decaying function. And the tail gets closer to 0 much faster than the parabola goes up. So in the end, we should expect a function that looks like that. Does that seem reasonable? What would happen if you multiplied a parabola times an exponential function? The exponential function and the parabola both are increasing over here, so the end result would be increasing. But over here, the tail of the exponential function is a whole lot shorter than the parabola ever gets. Which is weird, because you're like, well, the parabola gets infinitely tall. But the exponential tail gets infinitely close to the x-axis in a much stronger way than the parabola does. So let's look at the graph real quick, just so we all agree what the graph looks like. And there it is. So, yep, it goes up to the right, and it follows the exponential tail to the left. Now you might say, what's the difference between that and not even having the parabola there? So I'm going to raise the parabola to the power of 0 real quick, just to get rid of it. And does it look a little, wait, yeah, that's the power of 0. How does it compare when I get rid of the x squared? Yeah, it seems the parabola serves to squash it down a little, or yeah, without the parabola, the exponential graph is actually higher. Oh, and you know what, that would make sense, because the parabola is at 0 at the origin, whereas the exponential function's at 1, and when it multiplies 0 times 1, 0 wins. And so by having a parabola in there, when you have a parabola in there, it definitely brings the value of the function down. Now, we're just kind of talking about what happens when you multiply 2 functions together. If it doesn't make sense, it's no big deal. The point is just, we have 2 functions here, and that's what it looks like. So if you just looked at this function from far away, anybody would say, yeah, sure, it goes up to the right, and it's an asymptote to the left. And if you didn't zoom in or do any careful analysis, you might think that's exactly what it looks like. You might even think it looks just like any exponential function. Like, here's the exponential function to the x. And so we're basically just saying, yep, it goes up to the right and it goes down to the left. So what calculus does is it provides us with some insight to look more deeply. So, for instance, you know, how many people would think, hey, let's zoom in, see what's happening? Maybe all of you. You're like, hey, Mr. G, I'll zoom in. Let's zoom in. That sounds good. So let's zoom in. What happens when we zoom in? Well, now look at that. It goes up just a little bit before coming back down. And in fact, I can mess with my axis just a little bit. I'm going to go left 1, right 0.2, and then my y-axis, I'll just go down 0.1, and then I'll go up 0.1. Oh, and now that's a little bit more pronounced. In fact, I could mess with it even more to make it even more pronounced. I could go down 0.05 and up 0.05. And now, I mean, this is a very different looking curve than what we originally saw. And in fact, now there's a lot of details. We could say, hey, there's a maximum right there, and there's a minimum right there, and it's concave down over here, and it's concave up over here. So all of a sudden, now there's a lot of feature that wasn't immediately obvious to us when we just graphed it and looked at it from very far away. So calculus provides a tool to know when you should zoom in or not, right? So that's what we're going to be doing on this graph. Now, everybody, let's go ahead and draw this. Let's draw that sketch, and let's think about what we would expect to find from a full analysis of this graph. So I'm going to make myself a nice little graph right here. So I've got my, you don't need much to the right. You just need the graph going to the left, really. So it definitely hits the origin and then goes up. And then it goes to the left, does a little speed bump, and then comes back down as an asymptote. So everyone draw something that looks like that. Again, it's basically parabolic or exponential to the right. No surprises there. But then when you leave the origin, it goes up like a speed bump, and then back down like a speed bump, and then it asymptotically approaches the x-axis. Now I'm going to use a little bit of color to start identifying different features. So first of all, we can ask 3 questions. When is f of x equal to 0? When is f prime of x equal to 0? And when is f double prime of x equal to 0? These are kind of the 3 fundamental questions that we ask. Previous to calculus, you only ever really ask this question. But then in calculus, we ask these 2 questions as well. So what is f of x equal to 0 asking? When is the y value equal to 0? That means when is the height equal to 0? That means you're looking for an x-intercept. How many x-intercepts do we have? Yeah, just the one. That's it. Because over to the left, it's an asymptote. Over to the right, it goes up in space. So we have one x-intercept, and there it is. And then what is f prime looking for? When is the slope 0? And those are flat spots. And we have a couple of those as well. So I'm going to go ahead and mark them. I've got this maximum right here. There's a max. And I've got this one down here. That's a min. Okay. All right, now what is f double prime of x looking for? That's looking for inflection points. So where are those? This is going to be a little bit more tricky because we can't, we can't really identify an inflection point. Like you could obviously identify an x-intercept. An x-intercept goes through the axis. It's obvious. A flat spot is flat. It's obvious. An inflection point is a little less obvious. So what I recommend you do is I would start by tracing out parts of concavity that are obvious. So for instance, this is concave down. That seems very obvious to me. I got a concave down portion. And then where's concave up? This is concave up. That seems pretty obvious to me. So somewhere there between the transition of purple to black, I must have an inflection point. And then likewise over to the left, this lead up to the speed bump is also concave up. So that seems pretty obvious. So I've got a concave up portion here, concave up portion here, and then a concave down portion here. And so where are our inflection points? Kind of there, right? Like kind of right here, we put a little question mark, and kind of right here, put a little question mark. Okay. How does that feel? Yes, Henry.
So, like, there's two asymptotes, right?
There's just one asymptote over here. I don't believe this is an asymptote. It's going to keep going up and to the right, up and to the right, up and to the right.
Like, at what point is, like, the function that's going toward the asymptote is considered not concave?
This thing is going to be positive concavity forever. Yeah. The only way it could not be positive concavity is if it went straight, perfectly flat, not bent. And if at any point it became not bent, it would either stop approaching the x-axis and stay above it, a well-defined amount, or if it was tilted even a little bit, eventually it would hit the x-axis. So it's definitely still bent and it's a positive concavity. Good question. Anybody else? Okay, so what's our job then right now? What are we interested in? We want to find all those x values. I want to find this x value for the x-intercept, which is pretty obvious. It's just x equals 0. I want to find the x value for the minimum, which is still pretty obvious because it's x equals 0. I want to find the x value for the maximum. That's not at all obvious. I don't know where that is. I want to find the x value for that inflection point, and I want to find the x value for that inflection point. So what we're about to do is go through the process of setting all three of these functions equal to 0 and identifying those x values, which of course we can find by just looking at Desmos. But Desmos will only give you 3 decimals of accuracy, and doing the actual calculus, you'll get infinitely many decimals of accuracy. All right, so everybody ready? Now, let's read the instructions. So, consider the function. We just considered it. We considered it a lot, didn't we? We really considered it. That's what it means to consider something. Spend some time with it. So, f of x has 2 inflection points. Do we agree? Yeah, we have 2 inflection points. We're going to call them C and D. So everybody go back to your graph. We're going to call this inflection point C and this inflection point D. And they're telling us to label them such that C is less than D. And did I label it such that C is less than D? Okay, good. We're doing everything correct so far. So that's the first thing I want us to do is just find C and D. And then, for each of those intervals, tell whether it's concave up or down. Well, this is already something we can answer right now. Because on the interval from negative infinity to C, which is here, is it concave up or down? It's concave up. And the interval between C and D, is it concave up or down? Down. We already know the answer. And from the interval from D to infinity, is it concave up or down? Up. Okay, wonderful. So we already know how to answer these 3 questions because we drew a nice graph. And all we really need to do is find C and D. But we're going to do a little more. We're going to say f prime of x equals 0, and then we're going to say f double prime of x equals 0. And in fact, we'll begin by setting f of x equal to 0. So, because this is the subtitle of the course is Advanced Techniques for Algebraic Manipulation and Simplification. So let's remember how to do algebra. So f of x is x squared times e to the 10x. And I want to know, when does that equal to 0? How would you go about solving this problem for x? I think we all feel very comfortable with problems like 3x plus 5 equals 10. Right? You move the 5 over, you divide out the 3, that's algebra. But in this case, what do we do? We have an x in 2 different locations. How do we isolate x? I mean, theoretically, to get the x, if you just had e to the 10x equal a number, you would technically have to do a logarithm. You'd have to rewrite it as log base e of 5 equals 10x. And then you have the x all by itself divide out the 10, and then you have something like this. And so x equals log base e of 5 over 10. But we don't just have e to the 10x, we have e to the 10x times x squared, which is a lot more difficult. So at face value, I'm trying to suggest to you that this looks really hard. But then I'm about to say that it's actually really easy. Josh.
So we just divide by x squared on both sides of the
Well, that's an interesting idea. Can we just divide off the x squared? Yeah, that's an interesting idea, Josh. The idea had not occurred to me if you just divide off the x squared. Okay, because then you essentially just changed this equation into e to the 10x equals 0. And this graph is different from this graph. We already kind of, I mean, we know what this graph looks like. There's an x-intercept. Whereas if I just got rid of the x squared, what does that graph look like? Everybody, an exponential graph looks like that. Is there even an x-intercept? No. So we know for sure that this thing has an x-intercept. And if we just divide off the variable, then, yeah, then this wouldn't even have a solution because there's no x-intercept. But that was a nice idea. I like that. What else could we do?
I think x squared 0.
Right, if you let x equal 0, we know that x equals 0 is a solution by inspection. We can just say to ourselves, well, gosh, if I want this thing to equal 0, if I just let x equal 0, that'll work. And in fact, that is our only x-intercept. But it'd be nice to bring a little rigor to this. How do we solve things algebraically? There's a well-known rule called the zero product rule, which allows us to solve all quadratics and other formulas. So x squared plus 7x plus 12. You'll recall if I want to know when that is equal to 0, I factor it. So what multiplies to make 12 that adds to make 7? X plus 3 times x plus 4. And now, because I have a product, something times something equals 0, I'm allowed to say either that has to equal 0 or that has to equal 0. And so then I break it apart into two problems. Either x plus 3 equals 0 or x plus 4 equals 0. Move the 3 over, move the 4 over. Now I know for sure the answer is x equals -3 or x equals negative.
So you just
Absolutely. Because this is set equal to 0, which we are always allowed to use the zero product rule. All three of these are set equal to 0. So the zero product rule is a major tool. So we just say, well, this times this has to be equal to 0. Therefore, either that equals 0 or that equals 0. Are you all convinced? Yeah, I mean, this is part of why we always ask the question equals 0, because then you're allowed to use the zero product rule, which is a massive tool for solving for x. So now that you've done that, this is very simple to solve. You just square both sides and say x equals 0. And this one we already know. Will that ever equal 0? No. And you can even prove it to yourself by doing the logarithm. You can say log base e of 0 equals 10x. And as soon as you type log base e of 0 in your calculator, you get an error. So that's undefined. But you also know that there's no solution because solving for x means find the x-intercept. And in an exponential curve, there is no x-intercept, therefore there is no algebraic solution. Okay, well, we did the first one. We set f of x equal to 0, and now we know for sure x equals 0 is the only time that the function equals 0. So there's our x-intercept. So you can say x equals 0 is our x-intercept. Okay, that's result number 1. So now let's set f prime of x equal to 0. By the way, I totally realized that there's not a lot of room for you to do all this. Well, I just realized it right now. So if you want to have a separate sheet of line paper out, but who knows, maybe you can still do it. So we want to set f prime of x equals 0. Do we already know what f prime of x is? No, because we didn't do the derivative yet. But we can do the derivative. The derivative, it's a product rule. So remember to set yourself up. It's something times something plus something times something. And we do the derivative of the first times the second plus derivative of the second times the first. So derivative of the first times the second plus derivative of the second. What's the derivative of e to the 10x? Yeah, the derivative of e to the x is e to the x. But this is a chain rule because we have an inner function, right? So remember the chain rule says take the derivative of the outside. So the derivative of e to the 10x is e to the 10x. Leave the inside alone. And then multiply by the derivative of the inside. What's the derivative of 10x? 10. And so our derivative is 10 e to the 10x. So that's the derivative of e to the 10x, 10 e to the 10x. So the derivative of the second times the first. So far that's our product rule. What can we do to clean that up? We've only done this particular technique once, but there's something in particular that we can do with the e to the 10x. What is it? Yeah, we can take out e to the 10x. So we're going to factor e to the 10x all the way out front. So that leaves behind here just 2x. And then what do we have left? If I take out the e to the 10x, I have 10x squared. Okay. Well, for sure, that's f prime of x. And what we'd like to do is set that equal to 0. We set it equal to 0. A, because setting a function equal to 0 allows you to find x-intercepts, flat spots, and inflection points. But setting it equal to 0 allows you to use the zero product rule. So now I have this times this equals 0, which means either this is 0 or that is 0. And that allows us to break that long equation into two separate equations and solve them each separately. So when is e to the 10x equal to 0? Never. So that's never. However, when is 2x plus 10x squared equal to 0? Probably a couple times. So looking at this, you could either write it in the correct order, 10x squared plus 2x plus 0 equals 0, and do the quadratic formula. Now you can do the quadratic formula. Or you can try to factor it. Or, since there's only two terms, you can actually just factor it. So what can I take out from both of those?
2x.
Yeah, I can take out 2x. That leaves behind 1 plus 5x. And by factoring, wait for it, what can we do again? Zero product rule again. Wow, that zero product rule sure is handy. Thanks, person who invented zero product rule. It takes big functions and breaks them down into chunks, and you solve each chunk independently. So now what does that mean? X equals 0. That's one of our, what are we solving for again? F prime of x equals 0, we're solving for flat spots, right? So one of our flat spots is at x equals 0, which we knew. And the other flat spot is at negative a fifth, or negative 0.2. Well, now this is really exciting. We can go ahead now and go back to your diagram that you built, and I can now definitely label that my minimum was at 0, which of course we already knew. But now my maximum, we didn't know what that was. It's at negative 0.2. So we're keeping track of our results on our diagram. The diagram is ultimately our final answer. Everything that we're doing here is just work. But the diagram is going to communicate clearly our final answer to anyone in our audience. Now, that, by the way, is the one other thing we could check on Desmos. So on Desmos, I can come over here and look for my maximum. And where's my maximum? Negative 0.2. Wait, can you even see that? There. Yeah, so indeed, so far so good. We found all the right information, and calculus has led us there. All right, so now we're on to our last question, f double prime. So now we'd like to find f double prime. Set that equal to 0. I need a little space. I'm going to start over here. So now I want to find f double prime and set that equal to 0. Well, first we have to find f double prime. So what is f double prime? I'm going to write down f prime one more time real quick, just so I have it here so I can look at it. So f prime is e to the 10x times 2x plus 10x squared. And I'd like to take the derivative of this function. And this function is a, we'll need to use product, quotient, or chain. Product rule, because we've got something times something. So we want to find the second derivative, and we have to do the product rule, so that's something times something plus something times something. That's the product rule. Derivative of the first times the second plus derivative of the second times the first. This should be pretty straightforward. The derivative of the first, remember, is what's the derivative of e to the 10x? 10 e to the 10x by the chain rule. So derivative of the first times the second. And then derivative of the second, what's the derivative of 2x plus 10x squared?
2.
Yeah, 2. Derivative of 2x is 2. Derivative of 10x squared is 20x. So the derivative of 2x plus 10x squared is 2 plus 20x. Derivative of the second times the first. And what can we do to clean that up? The same trick. We could pull out we could bring out the e to the 10x. And that will allow us to clean out considerably what's going on inside. So we're going to bring the e to the 10x out front, leaving behind everything else. So from this chunk, I took out e to the 10x. What do I have left? 10 times this thing. So I've got 10 times 2x plus 10x squared. And then over here, once I take out the e to the 10x, what do I have left? There's 2 plus 20x. How does everyone feel about this? You'll notice we're already done with the derivative. And in fact, calculus was just the product rule. Derivative first times the second plus the second times the first. From here on in, we're just doing advanced algebra. Right? So now what can I do to clean up in here? And distribute and combine. So we still have e to the 10x. And then distributing, so I've got 20x plus 100x squared plus 2 plus 20x. Then I need to combine like terms. I've got two 20x's. So this gives us a final answer that f double prime of x is e to the 10x times 100x squared plus 40x plus 2. Now that was just finding f double prime. We had a goal. Our goal was to set f double prime of x equal to 0 and solve for x. So isn't this marvelous? We've done all this algebra, and we're just now getting to the part of actually setting it equal to 0 and solving for x. So once again, we have a product that's multiplied equals 0. We can apply the 0 product rule. When is e to the 10x equal to 0? Never. It's an always positive function. However, this is equal to 0, and you probably have to do the quadratic formula. Or maybe it's factorable. I don't know. But we set that whole thing equal to 0, 100x squared plus 40x plus 2 equals 0. And now you're just applying basic quadratic theory. You're just saying, hey, when is that quadratic equal to 0? So when is it equal to 0? What should we try? Should we try factored? Does anyone think that thing is factorable? Or should we just go into the quadratic formula and be done with it? I'm a little curious because at the very least, can't we take out a 2? I mean, it's not much, but maybe that would apply some new insight. If I divide everything by 2, now I have 50x squared plus 20x plus 1 equals 0. Now let's keep in mind that whatever the solutions to this are, what are we about to find? What points on our graph? The inflection points. And taking a look here at our graph, the inflection points are to the right and left of negative 0.2. Do we think our answer is going to be a whole number? No, D definitely is not a whole number. It's between negative 0.2 and 0. And that one's probably not a whole number either. So is this thing factorable? No. Probably not. But I mean, who knows? I don't think it's factorable. But is it? What multiplies to make 50 that would add to make 20? I don't think much. 1 and 50, 2 and 25, 5 and 10. I don't think that anything's going to add to 20. Okay, so we just have to do the quadratic formula. So everybody, here we go. Quadratic formula, A is 50, B is 20, C is 1. So quadratic formula, negative b plus or minus root b squared minus 4ac all over 2a. So that gives us negative b plus or minus square root b squared, 20 squared is 400, minus 4 times a times c, 4 times 50 is 200 times 1, 200, all over 2 times a, 2 times 50 is 100. So that gives us 20 plus or minus root 200 all over 100. Now I'm really kicking myself now that I should have told everyone for sure to do this on a separate sheet of line paper, but I think almost everybody is. Because I realize now this is a very long problem, isn't it? It's a very long problem.
Is it a negative one?
Where? Oh, you're right, negative one. Negative. Henry?
I don't want to be a downer, but did you ask us to do this, really?
Well, we do have to find C and D, and this is finally what we're doing. It says it has 2 inflection points in C and D. Yeah. This is the one part that they did actually ask us to do. But we stopped along the way and solved f of x equal to 0, f prime of x equal to 0, because those were good practice lead-ups to this. Yeah. Not a downer. It's a fair question. Okay, so at this point, could we just get a decimal? We just square root 200 and we get a decimal. And then we do negative 20 plus or minus that decimal over 100. We get 2 decimals. And those decimals would be our answer. To be fair, it is possible to simplify the root 200. And again, this is why this class is subtitled Advanced Techniques for Algebraic Simplification and Cancellation. So root 200, you ask yourself, what square number goes into 200? 100. 100 is a square number, and that's 100 times 2. And that allows us to break it up into root 100 times root 2. And so square root of 100 is 10, and that's 10 root 2. So now I can write down negative 20 plus or minus 10 root 2 all over 100. I mean, it's simplified more, that's what a professional would want, is a simplified answer. Can we simplify now the 20, the 10, and the 100? All of those whole numbers are divisible by 10. So we can go one step further and say negative 2 plus or minus 1 root 2 all over 10. Now at this point, we're definitely done in terms of simplifying. But we still now need the decimal. We want to know where those numbers are. So you would take your calculator and you would do 2 different computations. You would do first parenthesis negative 2 plus root 2 divided by 10, and then you would do negative 2 minus root 2 divided by 10. And when you type that into your calculator, make sure you use parentheses, because you want your calculator to do the entire numerator first and then divide by 10. So let's all try it and see what we get. Let's see. Parenthesis, negative 2 plus root 2, parenthesis divided by 10. Got negative 0.058. And actually, more typically takes 4 decimals. So 0.0586 is the first solution I got. And then negative 2 minus root 2 is negative 0.3414. Is that what anyone else got? Okay. This was a really good problem. This was a really good problem. I wish that, I had all of us doing this on a sheet of lined paper, that we had labeled everything really pretty, because this is the kind of thing you can hang up on your fridge. Right? It's a really good problem. And don't worry, we'll do another one like it. And I'll give you one like this on the test, where you walk your way through f of x equals 0, f prime of x equals 0, f double prime of x equals 0, and then you finish the whole thing with a beautiful picture, where you say, all right, my C and D were at negative 0.3414 and negative 0.0586. And we now know almost everything about that graph. What do we know about this graph? We know all the x values. So what would we want next? We want all the y values. Well, fortunately, that part's easy. You just take each of those decimals, plug it into f, and then that'll just tell you where the y coordinate would be. So that's not hard at all. You just take those x values, you plug them into the function, and then you would actually have coordinates. Which we should probably go ahead and do. Just to be, very, very done with the problem. So this first coordinate we all know is just 0, 0. That one's easy enough. If I plug 0 into the function, I get 0. But these 3, I'll have 3 different coordinates, because aren't you kind of curious? Are those 2 at the same height? Or is one inflection point higher than the other? They look like they're the same height, but then again, I drew it. Maybe I just had a bias and I drew them at the same height. So our function is x squared e to the 10x. So in your calculator, you would type, probably what I would do is put x squared e to the 10x into my graphing calculator. So x squared and then e to the 10x. I would put it in my graphing calculator, because then when you graph it, you can use the second trace feature, second calc, and the very first option is value, and I can just type those values in, and it's much faster than trying to input all that. So right now I can type in negative 0.3414, and that tells me that this coordinate is negative 0.3414, comma 0.0038. So there's that coordinate. My maximum, again, I can just hit second calc value, type in negative 0.2. my maximum is at negative 0.2 with the maximum value of 0.0054. And then here's the really exciting part. What's the height of that one? I did second calc value, type in negative 0.0586, and I get my coordinate 0.006.0019. So in fact, how do those two heights compare to each other? Yeah, in fact, C is twice as tall as D. Look at that, 0.0038, 0.0019. That's twice as tall as that one. So my drawing was not very to scale. And that is very surprising to consider that that one is higher than that one. Okay. Now you might be saying to yourself, is this problem done? No. You might be saying to yourself, can we now check on the graph? So let's look on the graph and see if we agree with the values that we got. What was our inflection point to the left? Negative 0.3414. Okay, well, do you believe it? Does that look like the transition between concave up? Does it look to be concave up on the left? And does it look to be concave down on the right? Because I drew that vertical line there to show the difference, that concave up is on the left, concave down is on the right. And then what about our other inflection point? It was negative 0.05?
86.
0.05 what, 16?
86.
Oh, 86? Yeah. So do you also believe that? Does it appear to be completely concave down in between the blue and the green line? And then does it appear to be completely concave up to the right of the green line? And completely concave down to the left of the blue line, or concave up to the left of the blue line? Yeah. Yep. We really dived into that problem. And I would say that's a full analysis. That's a full analysis. So if you wanted to say to yourself, okay, well, what are the steps of a full analysis? So one is you'd find when f of x is equal to 0, and find that coordinate as well. So you find the x value, plug it back into the function, get the y value as well. Then get y. And then you would find f double prime of x, I'm sorry, f single prime of x equal to 0. You find those x values, and then plug them back into the function, and get that y value. And then you would find f double prime of x, solve that equal to 0, find those x values, and then plug it back into the function to get your y value. And then when you're done, you have all the coordinates of everything that's interesting. Now, do you all see on my graph that we have the coordinates for everything that's interesting? I have that coordinate, 0, 0. I have that coordinate, negative 0.05, 0.019. I have that coordinate, negative 0.2, 0.054. I have that coordinate, negative 0.24, 0.038. So that's a nice full analysis to get, not only do I know where all these things are, flat point, inflection point, x-intercept, but I also have the actual coordinate values for all of them. We should do like another one of those as a special homework assignment.
No.
No, I'm serious. I mean, if you can feel really good about this whole process, then you will have just increased your confidence in your ability quite a bit. Because I know that was a long problem. All right, well, like I said, we'll do more of those. And I think right now is a great time to take a break so everyone can go cry. Get a sip of water. And then when we come back, we'll look at 2.7, which is basically more of this. So the time is 11:51. Let's be back at 12:01. I tell you what, here's what I'll do. I will write up this problem. I'm going to write it up real nice and neat on a sheet of paper. We'll take 2 sides probably. Write it up real nice and neat. That way you can all have it as a study guide. Is that better? Is that good? Would everyone like seeing that? I mean, you all wrote it down just now, but it'd probably be nice to see one more full and complete example. What does f of x represent? The y coordinate, very good. I put you on the spot, Fatima. I did put you on the spot.
I don't know, I was like, I was so embarrassed that you.
No, it's okay. I know I put you on the spot. I got you. I caught you unawares. It could happen to any of us.
No, no. Sometimes I don't get like the formula, but sometimes I can do because I practice too much. I usually don't know my answer. Now I know.
Yes, you do.
I have an idea.
Mm-hmm.
I think I could pass as faculty. I just started yelling at students in the hallway.
Is that how you perceive faculty? That we just go around yelling at students in the hallway?
I could do it.
Well, you could. I don't
Do you
know.
think they would believe me?
I mean, yeah. I mean, all you'd really need is just a name badge, and then that makes you pretty legit.
That's true.
And you could just put anything in there, like a bus pass or something. Just wear a lanyard. And there you go.
Well, yeah, I have a badge from Harvard.
Well, there you go. Yeah, they'd buy it. All right, folks, let's get going. So, taking a look at the picture on the screen, you don't have the vocabulary and understanding to see what we're looking at. So, what are features that we look for? Well, we look for x-intercepts, which that picture doesn't have any x-intercepts. We look for flat spots, and flat spots come in a variety of flavors, from just minima, maxima, or a transition point, or a flat photograph. And then we're looking for inflection points to kind of show where it changes from concave down to concave up, concave down, concave up. And these are the features that we're interested in. There are other features to be interested in about functions, but these are the primary features we're interested in using the function, the derivative, and the second derivative. And that's essentially what this class will be focused on, is what are features of graphs and functions that we can find by utilizing the first and second derivative. So, the major tool that we're going to think about, and especially going back to that graph I just showed you, where when we first looked at this graph, I wonder if I can just leave it and start over. There we go. So there, see, when we first loaded up the graph and just looking at it, you'd really have no idea that there were any interesting features to notice. Whereas, you know, on the one hand, you could sit there and you could fiddle with the graph and you could zoom and zoom and zoom, and maybe that would show you something and maybe it wouldn't. You know, I think we asked this question last time, how do you know how far to zoom? You know, should I keep zooming? Should I zoom for another hour? Should I zoom for another 2 hours? Like, how long would I have to zoom in or out to find the interesting feature? Whereas, by just computing the first and second derivative, it just tells you where those features are. And now you know automatically, hey, that feature is there, it exists, and I know I should go zoom to look for it. And by using this technique, you can actually find where those things are. And that'll give you an idea of how much to zoom. So that's what this chapter for sure is about. It's saying, how can we go find those interesting features? How can we go find the maxes and the mins without using a graph, or even if you did use a graph, how much would you have to zoom to find it? So I think we've already talked about a lot of this vocabulary, so I'm just going to kind of click through the screen here because we've already defined a lot of this. Critical number is any time f prime of that number is equal to 0. So critical numbers are flat spots. I don't even think I'll necessarily read through all these definitions for you guys. But we'll look at these pictures. So for instance, in each one of these graphs, it says 2, 3 is a critical value. Is that really what they're saying? Oh, or it's undefined. Ah, okay, I'm glad I came back. Critical numbers are either when the derivative is 0 or the derivative is undefined. So what were 2 points that what are 2 features of a graph that we've seen that were undefined?
Asymptotes.
Asymptotes. And and a cusp. So we've got cusps, sharp corners, and asymptotes. So yeah, looking here, then for sure, a critical value is any value where the slope is 0 or the slope is undefined. So looking at these examples, you can see here the slope is 0 because it's flat. And here the slope is 0 because it's flat. Here, there is no well-defined slope. It's a corner point. And again, I would call that a teeter-totter point, because if I held a ruler up against that point, I would actually have a good range where I could tilt my pen, and there was no one well-defined tangent. Whereas with a smooth curve, there is a well-defined tangent. Whereas here, that's a teeter-totter point, so the slope is undefined. So that's critical because the slope is undefined. This, boy, that's kind of tricky. It's definitely critical because on the one hand, you say, yeah, it's a minimum, but in this case, that doesn't mean the slope is 0. There is no well-defined slope at that point. So this is a little nebulous, right? It's a critical point because there is no well-defined slope, and it just happens to be a minimum value. This one, there is no well-defined slope, and it's not a minimum value. So honestly, what I should do here is kind of expand this definition. We want to find points where each of these are either 0 or undefined. So we're looking at 0 or undefined for all of them. Because if it's 0 or undefined, we know that we're finding something pretty interesting, right? I mean, if the slope isn't 0 or undefined, then it's not very interesting. You're just kind of going up, or you're kind of going down, or you're kind of going to the right, right? But if the slope is 0 and fine, then you found something interesting. Okay. So what do we know then? If we played this game, that you're not allowed to look at the graph, and you're just trying to figure it all out by hand, then how would you know a maximum is a maximum? That's my question for you. Like, we all have eyeballs, so we can just look and say, it's a flat spot, and it's a maximum. But how would you do it using calculus alone without looking at the graph? You definitely would know it's a flat spot by saying the derivative is 0. But what makes this a maximum as opposed to a minimum? Nothing.
Values to the left and right.
Well, that's true. You can look at values to the left and right. So it's a flat spot, and then you can just look at the value to the right and left of it and say, hey, both of those values are a little lower, so therefore it's a maximum. That's one possibility. What's another possibility? Because both of these are flat spots. What makes this one a maximum and this one a minimum? What other feature can we look at? Yeah, concavity. So you can do a double test. You could say, hey, anytime I find that my slope is 0, I could quickly do a second derivative test. And if it's concave down, my 0 slope means that it's a maximum. And if I find a flat spot and I do my concavity test and it's positive, then my flat spot is a minimum. So that's how the two tests kind of go hand in hand, is that you can, again, it's all based on this idea that you're not looking at the graph. You're only looking at the function, right? You're only looking at your work on your paper and you're not looking at a graph. And if you did that, then it's called the second derivative test. Now, again, we could look at all of this, but I don't think we're going to read through all this. We're just going to try that. You can always go back through the textbook and read everything. Okay. So, to find extremes, yeah. Okay, so everybody, did you all pick up a number 2.7 as you walked in the room? All right. I'm leaving my graph up there because it's so pretty. And it's a representation and a symbol of what we're trying to do. Okay, so here we have a graph. And what's the immediate feature that you're all interested in? Yeah, that flat spot right up there. That would be kind of like where our attention immediately goes. And how do I know that that flat spot is a maximum? Because the graph is concave down. So that's how those two facts go hand in hand. So it says here, oh, the above is the graph of the derivative. So this is actually not the function itself. This is the graph of the derivative. Well, now that's interesting. How many critical points does the original function have? We have to go back and think about that again. So if you were looking at your original function and you wanted to find a flat spot, you would say, when is f prime of x equal to 0? Now this graph is f prime of x, and when does it have a 0 value? Twice, here and here. So do we all remember saying that once, that the x-intercepts of the derivative are the flat spots of the original function? So what does it say then? How many critical points does the original function have? 2. At x equals -4 and x equals 3. And that's actually the whole problem. So if you just want to make a note to yourself that the x-intercepts of the graph of f prime of x represent flat spots of the original graph f of x. Okay, well that's it. No that problem. Any questions or thoughts? All right. In number 2, it says, here's a function. It's a cubic, and they say it has 2 critical numbers. So going back now to our definition of a critical number is anywhere that f prime of x is equal to 0 or f prime of x is undefined. And it wouldn't hurt. We could draw little pictures next to all those to kind of remind ourselves. So it's 0 at a maximum, 0 at a minimum, 0 at a transition point, or 0 on a flat line. And when is it undefined? At an asymptote or at a cusp. Those are some nice little drawings to keep in mind. Now, will this function is a cubic? It's a polynomial. Will a cubic ever have asymptotes or cusps? This is a cubic graph. And cubic graphs typically just look something nice and smooth like this. So will a polynomials are just powers of x, like x squared, x cubed, x to the fourth, x to the fifth. Do polynomials ever have asymptotes or cusps? They never do. Polynomials are just nice, smooth curves that wiggle. And that's it. So we know already that we're not looking to set f prime of x equal to undefined. Where is it undefined? It's never undefined. It's a polynomial. You can always plug any number you want into a polynomial. Because you're not square rooting anything, so you can't square root a negative, and you're not dividing by anything, so you won't divide by 0. Polynomial has no undefined parts of the domain. Okay, well what they do want us to find is the critical points, which are when you set it equal to 0. So to find critical points, you take the derivative and set it equal to 0. So everybody go ahead and take the derivative. Did anyone else get 6x squared minus 16x plus 54? Okay. And we want to know when is that equal to 0. Now, notice, we're done with the calculus. From here on in, we're just doing algebra. Right? So what can we do first to set this equal to 0? Or what can we do to start solving? Then we can take out a 6 and divide everything by 6. So I'm going to divide by 6 all the way across because they're all divisible by 6. That gives me x squared minus 10x plus 9. And always your first question is it factorable? Because factoring is easier than the quadratic formula. So does anything multiply to make 9 that adds to make negative 10? Yeah. Negative 1 and negative 10. Negative 1 times negative 10 is 9. I'm sorry. Negative 1 and negative 9. Negative 1 times negative 9 is 9. And negative 1 plus negative 9 is negative 10. And now by the zero product rule, we can set both of those equal to 0. And you probably all know the shortcut that if it's just x plus or minus a number, you just change the sign and you call that the solution, right? We can just say x equals 1 and x equals 9. So at least in terms of just doing what this problem asked, we just did what this problem asked. The smaller one is x equals 1 and x equals 9. I have a problem. I tend to go beyond what the problem asks because there's a lot of interesting things to look at. But we're done with that problem, right? I mean, if all you had to do is input the numbers into the software, you'd be done. But because you're all so curious people, you're curious people or are you curious people? That means two different things, doesn't it? One means that you're filled with curiosity. The other is that I find you curious. Right? You're curious people. So what would that mean then? On my graph, I've got a 1 and a 9. And so our graph probably does something like that. So then what would we want to do next? All we know is that there's a flat spot at 1 and a flat spot at 9. Then we'd want to know the y-values. Right? What? I believe that's correct because it's a positive cubic. So it goes up to infinity this way and down this way. The only thing I don't know now is the overall shifting of that. I have no idea where that thing is. I have no idea how high up that is. I mean, this whole thing could be down here for all I know. I don't know until I actually plug it in and find out. So, for instance, then you'd be driven by curiosity to actually plug in these numbers into the original function. Where is this thing? The first one is at 24. And then if I plug in 9, that's negative 488. So my graph, I would need to adjust a little bit, and put that down there. Now see, wasn't that fun? That was fun. And see, now I can really finish the problem and say, I have a critical value, I have a maximum at 124, and I have a minimum at 9, negative 488. And even I don't have anything else to do at this point. Like, now the problem is really done, right? We've kind of said everything there is to say. Well, yeah, that's true. We could go find the inflection point, right? Oh, heck, we could spend another half hour on this problem, huh? But we're definitely done for now. All they asked was the critical values. Okay. Number 3, I believe, is asking a similar question. there. Yep. So it says, there, here's another function. Now this one's also cubic. Do I draw this one the same as the other one?
No.
This one's flipped upside down. So this one, my graph is going to end up looking something like that. Now, but do I really know where those maxes and mins are yet? No idea. All I know for sure is that I've got something that does this. I'll have a minimum, I'll have a maximum. I don't know how high up or down those are, and I don't even know where they are yet. But that's our curiosity. We're wondering, where is all of this? Now they're telling us that it's one local max and one local min. So that's good. We should know ahead of time. There's two solutions. So what do? Find the derivative. So we'll go ahead and take the derivative. So negative 6x squared plus 42x minus 36. Set that equal to 0. Once again, we can divide everything through by 6. Or better yet, by negative 6. So we get rid of that leading negative. So now we have x squared minus 7x plus 6 equals 0. And honestly, this is either insulting or very nice of them to give us such easily factorable functions. Right? This was really nice. They set this up for quick success. What do we multiply to get 6? They asked to make negative 7. Yeah, just x minus 6, x minus 1. By the zero product rule, either that is 0 or that is 0. So we say the values are x equals 6 and x equals 1. Well, I'm very pleased with that because my graph, I already kind of set it up to have values of 1 and 6. Notice that my graph is not to scale. Does it really matter that my graph is not to scale? No, the key thing is that if it's 1 and 6, I better have both of these points to the right of the y-axis, right? So we want to be accurate, well, we want to be realistic, but not necessarily, it doesn't have to be perfect. Okay, so now what would we want to know? Now we need to know the y value, and this one actually is asking for it. They're saying the function has a local minimum at what x value? 1. With the value, and by value, they mean y value. So they're actually saying the local minimum is at x equals 1, and the y value is, you have to go back to your function and actually type in 1, which is the original function. There should be like a joke that at the end of the problem, I say, what do you do next? And you say, plug it back into the original function. Because that's always how you finish. So now we have negative 2, 1 plus 21 minus 36. Did anyone else get negative 16? So back to the drawing board with my graph. The value was apparently all the way down to negative 16. So I do need to redo this now. So now I know that's where my minimum is. I'm just going to get rid of my graph because I don't know anything yet. And although I do know that it's going to go like that. Now I need to plug in 6. So again, if you're using your calculator wisely, at this point you just hit second enter. And it brings back up the same equation you just had. And you just go through and change all those 1s to 6s. And anybody, if you would like to know how to use your calculator more efficiently, I would really love to show you how to do it in my office hours. So now, when I plug 6 in, so the local maximum is at the value of x equals 6, and that has a value of 109. Did anyone else get 109? So now I know that that y value is way up here at 109. And now I know that my graph actually looks like that. And that's a much better looking graph. I can now say my coordinates are 1, negative 16, and 6, 109. Better.
And you determine which one was the one. Just because you do the shape of it.
Right, because we know that a cubic graph looks like this, and a negative cubic looks like this, we were able to make some assumptions. But if we actually wanted to verify that that was a maximum, we'd have to do the second derivative, plug in 6, and make sure the second derivative is negative. And if I really wanted to know that that was a minimum, I would need to do the second derivative and plug in 1 and make sure the second derivative is positive. Fortunately, we didn't have to do that in this case. But that is how you would do it if you were pretending not to know what the graph looks like. Yeah. Good question. All right, how does everyone feel about this? You're making your little sketches, you're drawing your graphs? Yeah, I know that, I know I've said this before, and I guess I don't ever get tired of saying it. There's a certain irony of all the work that we're doing, because we could do all of this on Desmos. We just go to a website and get all of this information, except for the inflection points, mind you. Desmos doesn't give you inflection points, right? You wouldn't be able to get inflection points from Desmos. But you'd be able to get all the maxes and the minimums and stuff like that. Okay, folks, number 4 is the same. Let's skip it. I mean, just together, you still do it. Like, do number 4, circle it, right? Homework. Well, let's keep moving along and look at another problem that's a little more challenging, because that one we've already essentially done. So do number 4 on your own. Now, even though you're doing all this work by hand, can you check your work by looking at Desmos? Yeah, I think that'd be a great idea. I mean, I could imagine, none of you would do this, but I can imagine there's a student who would go home and they're doing their more homework and they just take the function, plug it into Desmos, get the coordinates, and then plug it into plug it into more and then get the right answer. Again, none of you would do that, but I realize that it could be done. Okay, now this one's a little more interesting. Great. So the function 6x plus 7x to the negative 1. First of all, in a more friendly visual form, this is 6x plus 7 over x. What does that graph look like? Trippy? Is that what you said? Yeah, a little trippy. This graph is not so obvious. People don't walk around thinking, oh yeah, that's what that looks like. We all know parabolas and maybe cubic. So 6x plus 7 over x. So what does our graph look like? Like that. It looks like that. I'm going to make my window a little better. Oh, that looks very nice. Okay, this is a good looking graph. Isn't it pretty? I mean, I don't think we spend much time working with functions like that, but that's what it looks like. It's very nice. So what features do we notice?
There's a diagonal asymptote.
There is a diagonal asymptote, and the diagonal asymptote is in fact 6x. The 6x part of the graph is the asymptote, and the 7 over x part of the graph is the asymptotic part. So when you add an asymptotic graph plus a linear graph, you get a slant asymptote. Yeah, sure enough. Okay, so again, features that we're interested in: a maximum, minimum, an asymptote, and the fact that this down here is concave down, and this up here is concave up. Right? There is no inflection point, is there? Because the changeover from concave down on the left to concave up on the right, the changeover is the asymptote itself. So there is no inflection point. However, we would still be able to say, when is the second derivative, not when is it equal to 0, but when is the second derivative undefined? And that's telling you the changeover from the negative concavity to the positive concavity, because you're finding when the second derivative is undefined, which is at the asymptote. So the asymptote still does represent a changeover from negative concavity to positive concavity. Yeah. How does all that feel, folks? Let's make a quick little sketch. So draw that. Let's make a nice little sketch. So all of our graphs will look something like you have a graph that looks like that. You can make your graph look more realistic by keeping in mind that it's a vertical asymptote riding along the y-axis. So the y-asymptotes, those are vertical asymptotes, whereas these other asymptotes are going along the diagonal line 6x. So that's what we're looking at. And now again, like let's say you're on a first date, and this is all you have on the table in front of you at the restaurant. There's this graph. You can spend at least 2 minutes talking to your date about what you see on this graph. Right? You can say, oh, look at this. It's an inverse graph, first of all. And there's a slant asymptote, a slant asymptote. And then you can say, well, there's a maximum value there and a minimum value here. And this is negative concavity here. This is positive concavity here. Oh, positive concavity. And furthermore, the slope is positive, 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 negative, 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 positive, positive, positive. Okay, so maybe that was only a minute. And I don't know if you'll get a second date. But there's a lot of features, right? There's a lot of features. So we're just going to find a couple of features. It says here that it has one local minimum and one local maximum. We already completely know that by looking at the graph. So where are they? So how do we find them? How do we find the critical points? Set the derivative equal to 0, or set the derivative equal to undefined. That'll be fun. So on the one hand, let's just find the derivative first. So using the original form here, the derivative of 6x is 6, and the derivative of 7x to the negative 1 is what? Minus 7x to the negative 2? So that's the derivative. Let's clean it up. The derivative is 6 minus 7 over x squared. Okay, so that's a nice clean form of the derivative that we can now do computations with. And we're going to do two things. We're going to set it equal to 0, and we're going to set it equal to undefined. The word undefined. All right, so first let's set it equal to 0. So when do we know when that thing will be equal to 0? X is in a weird place, isn't it? It's in the denominator. How do we get x out of that denominator and solve for x? The first thing, put it over to the other side. So we have 6 equals 7 over x squared. Then what? Push it up? Oh, by making it a negative exponent? You could, but it delays the need to still solve for x. So what's one other thing we could do right now? We want to get x out of the denominator. Yes, we could multiply both sides by x squared. And why will that be helpful? Yeah, because it cancels the x squared from that side. So isn't that interesting? When you ask the question, how do you get x out of a denominator? You cancel it. That's what you do. You destroy it. And now it's gone. It showed up over here. So now we have 6x squared equals 7. And now this is just a normal algebra problem. We can all finish solving this. X is being squared multiplied by 6. You divide by 6. You get the fraction 7/6. And then x is being squared, so you square root both sides. And we get x is equal to plus or minus the square root of 7 over 6.
Why is it plus?
Whenever you do a square root as an action step in the process of algebra, it is always plus or minus. And by action step, I mean like here, when I divided 6 on both sides, that's an algebraic action step. You're doing something with both sides. It's like the old balance scale concept, where you have a balanced scale. You'd have to add a rock to both sides to keep it balanced. So when the square root is the action step that you're doing to both sides, the square root is always plus or minus. Does that answer your question? I don't think so, because I just gave you a rule. The reason is because if I wanted to square something and make it equal to 7/6, what could I put right there? I could put positive root 7/6. Would that square to make 7/6? Yeah, because the square and the square root cancel. Whereas couldn't I also put in negative root 7/6 and square it to get 7/6? Are both of those valid things that I could square to get 7/6? Because a negative times a negative will be positive. That's why it's plus or minus. Because there are, in fact, two objects that if you square them, you get 7/6. Okay, well, wonderful. So I'm sure we're all curious to know what that decimal approximation is. So the square root of 7 divided by 6, I get a decimal of about 1.08. So x equals, well, x is approximately plus or minus 1.08. And then we would go to our graph, and we would say there's a minimum at 1.08, and there's a maximum at negative 1.08. And of course, we're not done, because we still have to take those two values and do what with them? Plug it back into the original function. That's always going to be our joke answer. What should I do now? Plug it back into the original function. Because we want to know the value, and in fact, the question is even asking for it. So they're even saying the local minimum is at the x value of 1.08, and it has a value it's a very poorly worded question. Value means y value. That means the y value. Because they're asking for a coordinate. So now we need to plug 1.08 back in, or we need to plug root 7/6 back in. Yeah, I mean, it'd be better to plug root 7/6 back in, because then it's more accurate. So back into our original function, we're going to do f of root 7/6, which would give us 6 times root 7/6 plus 7 over root 7/6. Well, that's very ugly. Right? And what are we going to do? We're just going to compute a decimal out of it anyway. And I suppose it would be possible to find a common denominator and actually add those together. I'm not asking you to do that. It'd be terrible. It'd be truly terrible if you wanted to arithmetically simplify that. I'm not asking you to do it. So you should think, boy, Mr. G, you're very kind and gracious. You're not making me simplify that. So instead, we would just do it on our calculator. So you have 6 times that thing plus 7 divided by that thing. And I got 12.96. Did anyone else get 12.96? Oh, good. Now that was just for the positive. What if I plug in a negative? Let's just reason this out. If I just change that to a negative, then this term becomes negative. If I put a negative, that term has become negative. And therefore, the whole thing should be negative 12.96. So now that one is negative 12.96. And now we have our 2 coordinates. So this coordinate is 1.08 comma 12.96. And this coordinate is at negative 1.08 and negative 12.96. All right. That's an interesting looking graph. How does everyone feel about this process of finding a max and a min? We haven't done a second derivative test. You know, we've just looked at the graph and we knew that was concave up and we knew that was concave down. But at some point you might be confronted with a mystery function and you don't look at the graph. And then you have to be able to say, well, was that concave up or concave down? Okay. Number 6. Given the function, it's a cubic, find the first derivative. Where does it have a min or a max? I think we've already done a problem like this. You just take the first derivative, set it equals 0, solve for x, and then plug it back in. So I'm going to say number 6 is for you to do as well. Nothing new there. Good practice, this procedure of setting it equal to 0, solving for x, plugging it back in. That's a procedure we'll do over and over. Okay. This is a slightly different question. We'll have a little fun with. Everything that we've been solving thus far have been local maxes and mins. A local max and a local min. Why do we use that phrase local max and local min? Like, let's say that I had a function that went like that. Anytime there's kind of like the top of a little mountain, we call that a local max. Because locally, is it the highest point that you see? Yeah, right there it's the highest point you see. Is it actually the highest point you see? No. What's the global maximum? This one. This one right here is my global maximum. Where's my global minimum? That guy? There's my global minimum. Of course, by using the word global, I'm making an assumption that that's all there is. This graph right there. I've shown you the whole thing. Because if I actually just do something to my graph now, like get rid of a whole bunch of it, and I say, where's the... Now, where's the... Much smaller. Where's the local maximum? That big. Where's the global maximum? Still that big. Where's the local minimum? Well, there's not a local minimum because there's not one of those guys. However, there is a global minimum. Where's my global minimum? That. So it depends on your view window of the graph when you ask the question global max, global min. It depends on, how much are you allowed to look at. So that's what we're asking in this graph. Is it says consider this function, which is a what? It's a, what shape is it? It's parabola and it's facing down. So we have some graph and we can immediately start by saying it looks like that. We'll actually graph it so we can see it. But they're telling us only go so far to the right as 2. So I'm going to stop the graph right there. And then only go so far to the left as -3. I'm going to stop the graph right there. And they're asking us, just look at that thing. Just look at that right there. Don't consider the entire parabola going out to infinity. Just look at that teeny little thing right there. Now, we could go ahead and just answer these 2 questions now visually. So where's the absolute maximum? The absolute highest point on this graph? Right there. Right, so that's my absolute max. Now, where's my absolute minimum? This thing, right here. Okay, so that's my absolute minimum. That's my absolute maximum. That was pretty easy to do because we had a graph. Now, which one of those two features can you actually find with calculus? A flat spot, setting the first derivative equal to 0. Which one could you solve by setting the first derivative equal to 0? Only that, because that's an actual flat spot. Is that a flat spot? No, so we wouldn't have been able to find that using a first derivative. Rather, the whole point of this question is to say that if you're interested in absolute maxes and absolute mins on a predetermined arbitrary window, then what you do is you do calculus to find any flat spots, and then you simply plug in the endpoints and see how high and low those are. And that's it, you just check the endpoints. That's kind of the whole purpose of this question, is to say, do your calculus, find the flat spots, but then also check the endpoints to see if maybe the endpoints are higher or lower than your little maxes and mins that you found. So let's go ahead and do that process. We have our function. Let's go ahead and do the first derivative first. Oh my gosh. We never even finished that last problem. Remember, we were going to set it equal to undefined? We never set it equal to undefined. We'll have to go back. Let's finish this though. So first derivative, what's the derivative of 1? Nothing, yeah. And then that would be what, negative 10x squared? No, negative 10x. So there's our first derivative. We'll set that equal to 0. That's a nice easy function to solve for x. We divide off the negative 10. And b, we have a flat spot at x equals 0, which we kind of already did from our graph. The flat spot is indeed at 0. So because we used calculus, we know this is a genuine flat spot. Also, folks, just for fun, let's confirm, let's use the second derivative test for once. So what's the second derivative? What's the derivative of negative 10x? That's just negative 10. And if I plug in 0 into this function, so the second derivative evaluated at 0 is just negative 10, which means it's concave, what, up or down? Concave down. So that just confirms for us that this graph is indeed concave down, and therefore that really is a maximum. So that's why we use the second derivative. We just calculate the second derivative real quick, plug our flat spot into it, and just confirm is it concave up or concave down. Because now that I know it's concave down, I draw a little thing that's concave down, and I verify for myself, yeah, for sure that thing was a maximum. It was a maximum. Okay, so let's say that we didn't already have a graph, but we wanted to start drawing a graph. I would say, well, I know for sure. Okay, now if I take my 0, I have a flat spot there, it's a maximum. Plug 0 back into the original function. So what happens if I plug 0 back in the original function? It would just be 1 minus 5 times 0, which is just 1. So now I know for sure that I have a maximum at 1. Right? And I can start drawing my graph. I don't know what the rest of my graph looks like yet, but I can start drawing it. Now let's do the whole endpoint idea. What are my 2 endpoints? Yeah, negative 3 and 2. So I'll go ahead and solve both of those as well. I'll do f of negative 3. Means I'm going to plug 1 minus 5 times negative 3 squared. That'll give me a coordinate. And then I'll also do f of 2. Plug in 1 minus 5 times 2 squared. That'll give me another coordinate. So the first one, negative 3 squared is 9 times 5 is 45. 1 minus 45 is negative 44. So now I have input, output. I have a coordinate, negative 3, negative 44. So I come all the way down here to negative 44, and I put it back. And there's that part of my graph. And then my second coordinate at 2, that would be 2 squared is 4, 5 times 4 is 20, 1 minus 20 is negative 19. That tells me I have the coordinate 2, negative 19. So I'm going to go much higher up, negative 19. And there's my other point. Right. So I have this coordinate, 0, 1. I I have this coordinate, 2, -19. I have this coordinate at -3, 3, 1, 3, 4. What do you think of my graph? It's what, Josh? Oh. Okay, I wasn't expecting that answer, but okay. I suppose I could make it better, huh? I could make it look better if I had a little bit more forethought and I knew what exactly I was doing. I could have done like that, like that. Take a little more time. So there's one coordinate, there's another coordinate. Oh wait, Josh, were you saying that my graph was weird or the B graph was weird? Should I take that personally, or were you just talking about the graph?
Just talking about the graph.
Oh, okay. Okay, is that graph better? Okay, yeah, that's definitely a lot cleaner. Okay, so now we're done, and we can answer the question. Where's our global maximum? There. Where's our global minimum? There. And that's it. That's the end of the problem. So I would say where this question is coming from is, again, we constantly are playing this game. Pretend you can't look at the graph. Pretend you didn't have a graph calculator, you couldn't graph it, and you just wanted to know, theoretically, where are my highest and lowest points? And you'll notice I did all this by hand, by calculation. I knew that was a point, I knew that was a point, and I knew this was a point. And actually, just from those 3 points only, watch this, I could just make a graph with that point, and that point. And even if I didn't pretend to know that it was a parabola, I would still know that those were my points to choose from. Global max, global min. Even if I didn't really know what the graph looked like. So, okay. I believe the next question is the same.
So the maximum is 2 and
Yep, the global max would be 0, 1. Oh yeah, I'm sorry, the absolute max is at x equals 0. Oh, but it asks for the absolute maximum value is 1. And it occurs at x equals 0. And then the absolute minimum value is -44, and that occurs at x equals -3. Does that work? You know how my phone always goes off 5 minutes per day in class? I wonder if I turned that off. Anyone would notice. I could like just keep working for a good 20 minutes, 30 minutes. Would any of you notice? Do you check your phone? I don't know. I should try that one day as a prank. I wonder if we have class on April 1st. I'll try it out. Okay, here's another example. Number 8 is just another nice example of trying to get at where are the minimums, where are the maximums, where are the global maximums, where are the global minimums. And all it means is check your endpoints. After you do your calculus, check your endpoints. So let me see. I think that we could successfully move this one up too. Let me check to see what else we have on here. Oh, that's it. Well, we have 5 minutes. Let's finish it. Oh, how exciting. We finished it. We normally have like a problem or two left at the end. Not today. We're all caught up. That's very exciting. So in this particular case, 6x squared minus 6x plus 7 is not as obvious to me where that parabola is. I know there's a parabola. I know it's facing up, but I don't know where it is. So let's try this approach where we don't even draw a graph, and we just go blind using calculus and endpoints alone. So first things first, we take the derivative, which is what, 12x minus 6? We set it equal to 0. So then we know 12x equals 6, or x equals a half, or x is 0.5. Now I'd like you to just start getting in the habit. Anytime you solve for x, plug it back into the original. So like, I just solved for x. I know that this is a flat spot. I don't know what it is, a max, a min. But I'm going to go ahead and plug it right into the original. So f of 0.5 is 6 of 0.5 squared minus 6 of 0.5 plus 7. And I'll use my calculator to figure out what that is. That'd be a good habit to get into. Anytime you solve for x, from either the first derivative or the second derivative, just go ahead and plug it right into the original to find out where that coordinate is in space. I got 5.5. So we're going to start a graph. All I know for sure right now is that at the coordinate 0.5, 5.5, I have a point. And it's flat. So it could be a max, it could be a min. I just don't know. But I also know it's the only one. It's the only flat spot, which of course we know because it's parabola, and parabola only has one flat spot. So now let's check our endpoints. So at this point, I'm just going to plug in my two endpoints. What are my two endpoints? It's 0 and 6. So I'm going to keep doing my work right here. I plug in 0. That answer is obviously 7 because all the x terms go away. And then I plug in 6. My calculator already has the function there. I just hit second enter. And I change all my 0.5s into 6. That gives me 187. Yeah, I'm kind of tall. And now I'm going to make a new graph because I didn't like that one. Because my points are all above, so I can make the graph look like that. I've got a 0.5 at 5.5. And then I've got a 0 at 7. 0 at 7, that's just barely above it. And then over here at 6, I've got a point up at 187. So I've drawn my three coordinates. Only one is a genuine flat spot. The other two are simply endpoints. And at this point, I'm sure you can all imagine what the parabola looks like. Because we know it's a parabola and we know it's facing up. So could we all just kind of sketch in the parabola, making sure you put the flat spot at the bottom. This is what the textbook and this class calls curve sketching. You are the graphing calculator. So how do we answer these questions? The absolute maximum of f of x on this interval is at x equals 6. And it didn't ask for it, but with value 187. And the absolute minimum is at x equals 0.5 with value 5.5. I have a few tests to pass back to some of you. Didn't get your test the other day, so I'm going to give that to you. But otherwise, I'd say we're all done for the day. If you want to stick around, ask me some questions, come to office hours. Here's Fatima. Here's Rosa. Here's Juan. Here's Yorka. Sarah. And here's J.R. So this was the end of the week. We got through 2-7. So all of your homework due on Tuesday is 2-6, 2-7, and anything previous. Please come see me in office hours. Please email me with your questions online. Nothing makes me happier than getting emails from students on a Saturday night. What else do I have to do? Right? See you, Josh. Josh. Oh, Nando, you could have sold those on eBay or something.
It's just another piece.
But you still could have sold it. Yeah, you too, Nando. See you later. Sarah. Oh, I would love to show you your calculator. Ah, well, let's take a look. Here, That's terrible.
I don't know if it's because I don't know.
So, first of all, that's an impossible window because X-min and X-max, they mean how far to the left, how far to the right.
Obviously, this should be like.
That should be a negative and then a positive because you're going left to right. Min-max means left to right. Same thing for the Y. Min-max means down to up. So now you have an actual window. Now, just so you know, you can always, yeah, right. So let's keep talking. You can also hit zoom, and you can always do zoom standard. That'll immediately give you left 10, right 10, down 10. So that would have fixed your problem to have a normal looking window by hitting zoom standard. Okay, but now the question is, and Sarah, this is the mystery. This is the exciting part. Where's the graph and what does it look like? Now I could cheat and look at y equals and say, oh, well, I mean, I know what this is supposed to look like, so I know where to zoom. Well, let's say you don't know what it looks like and you don't know where to zoom. So what you do is you hit trace. It always starts with x equals 0. And you say, okay, well, there's 1. So now you start moving to the right, and you watch the y value. Okay. What's the y value? So now watch as I keep going. What's my y value? Positive and gigantic. Okay. We don't want to zoom all the way up there because basically we know what that's doing right now, right? It's just launching up. Now let's go back to 0. Now let's go to the left. What's my y value? It's really small. It's e to the negative 6. That means scientific notation 4.6 times 10 to the negative 6. That's teeny, teeny, tiny. Yeah, it's very small. So we know that there's not much point going much to the left. So the first thing I'd do is I'd say, well, I really only need to go left. You know, these numbers are so small. Left maybe 1, and then right maybe a half. So that's the first thing I'll do. I'll go left 1, and then right a half. Because now I'm just getting in that area that we're interested in. Okay, well then what? I know we remember that the y values are pretty small. So instead of going down 10 first, I don't have to go down 10. I'll just go down a little bit below the axis so I can see the axis. I like negative 0.1. So I'm just below. Now how tall do I have to be? I can start with just 1. Because we know that little bump was not very tall. So now it's like, now you see that I'm doing a lot of playing around. Okay, I don't see any features, right? So in other words, that bump is so little that going all the way up to 1 is too tall. I'm gonna go to 0.1. Now what do we see? Whoa, I see the bump now. Okay, now see, this is exciting, right? So we want to keep on fiddling with our window so I can keep zooming in. So instead of going left all the way to there, left to 1, I'm just going to go left 0.5. And I don't need to go up as high as 0.1 because that bump was very short still. I'll go up to 0.05. Okay, I see the bump. I don't need all this space down here. And I don't need it to be that tall. So I'm going to get rid of all that negative part down there, make that maybe 0.001. Really, I don't have to go down far at all. And then how far up should I go? Not 0.05, maybe just 0.01. Whoa, now, is that a good graph? Now, I don't even need all this space over here. So now I'm going to get rid of part of my x max and just do 0.1. I think that's far enough. Now, is this a good graph?
Yeah.
This is an amazing graph. I probably want to go to the left a little bit. So x min, I'm going to go just a little bit further to the left, maybe 0.7. Okay, I would say that this right here that we just came up with is like the best graph. Now, did you see how I did it?
Yeah.
It's called you play around for a while. It's an art, not a science. You just fiddle with it, you fiddle with it, you fiddle with it. And that's it.
Thank you.
Okay, go have fun with that. Try that on your own.
I will.
Now, Henry, I want you to know I felt bad. I immediately shot down your joke. You said, hey, I could go out there and pretend to be a teacher and yell at everybody. And I was